Today we're discussing solving systems of 3 equations and 3 variables using row reduction. Possibly from high school, we remember how to solve systems. Although in high school, there might or might not have been a systematic way of solving systems. Here we're trying to describe this row reduction method using an example, and then row reduction is a systematic way of solving systems, and it makes it easier to expand the method to equations of more variables and more systems of equations of more variables and more equations. To be able to use row reduction, I need to first describe row operations. What are row operations? Multiplying a row by a non-zero constant. So if I take any row in here and multiply each term of the row by any non-zero constant, and then replace that row by the new equation, that I've done a row operation. Interchanging any 2 rows. If I switch the order of the rows in any possible way, and that would give you an interchange of 2 rows. It is important for future linear algebra lessons that we remember that interchanging 2 rows as a row operation is just interchanging the order of 2 rows and not more than 2 rows. So if you interchange so that if you change the order of the system so that you need more than one of these to get that order, then it's not just one row operation, it's multiple row operations. The third row operation is add a multiple of a row to another row. So what I can do is I can multiply, for example, the first row by negative 2/3. That is each term in the first row multiplied by negative 2/3 on my piece of scratch paper. Then I add it to, for example, to the third row, and then replace the resulting equation for the third row. In this row operation, none of the other rows change. So when you're multiplying the other row by a constant, it would be on a piece of scratch paper. And then you, after you get a resulting equation, you replace it in here. The next thing is that how do we use row operations to solve the systems? First thing is how to do row reduction. To understand the row reduction, I do one definition for you: leading term or coefficient. The first term or coefficient in a row is called leading term or leading coefficient. Now, how do we use row operations? First important part is that when you do row operation on any system, the new system that you get will have the same set of solutions as the old system. And that's why we call a new system that you get by using any of the row operations or any multiple row operations in any order. The new system that you will get is row equivalent to the old system. So, and sometimes I will refer to the new system as the row equivalent system. Now, the row reduction is using row operations to create a row equivalent system where each equation's leading term is different from the others and equations are ordered by leading variables. What does this mean? For example, the leading term for the first equation is 3x. The leading term for the second equation is 7y. The variable in the first leading term is different from variable in the second leading term. And also, the order is correct. X for the first equation, Y for the second equation. And then the third row is not different from the leading term is not different from the first row, and the other thing is that it doesn't have the order is not followed neither. So basically, the order part will create an indented system of equations. So as you go, it has to indent in because your leading term moves on. And one more thing, what do I mean by the order? Usually you have either alphabetic order or numerical order for your variables. And here I'm following the alphabetic order. Another thing I want you to notice is that each term with the same variable is written underneath each other. Therefore, the second equation that was missing the term with x in it is indented in, so 7y can be written underneath the 2y. And so the other part is that the first description that I gave you is part of row reduction. Another part of the row reduction is this statement. If all leading coefficients are 1, then row reduction is done. And all the leading coefficient in what was described above that. Let's start with an example to see how this row reduction works. So I have this equation that a system of equations that I'm supposed to solve, and it follows that all the terms with the same variables are underneath each other, and the constants are underneath each other, equal signs are underneath each other, and I want to use row operations to create what I described over here. The first thing that you want to do is to create leading one in the first equation. If you have, your first equation is missing the first variable, you want to do interchange two rows first. But in here, my first equation is not missing the first variable. So instead, I'm going to just multiply the first row by a non-zero constant. And then I create a leading one for the first row. So, for example, if this was the first row, you should have used interchange two rows. But since the first row contains x, which is the first variable in that order, in alphabetic order that we have, I don't need to use the row operation number 2. I just need to use row operation number 1. So what do? My plan is to rewrite this equation using the first row operation. So the 3 turns out to be 1. How does that work? I should multiply the first equation by 1/3. So this is how I write it. Row 1, or equation 1, or row 1, multiplied by 1/3 should go back into row 1. Let's use scratch paper to do that. Row 1, multiply by 1/3. How do I write it? The other way of writing it is 3 divided by 3 is 1. So I write, and I don't need to write 1 times x, so I write x plus 2/3 y plus 5/3 z equal to 73/3. Now, this tells you, this is the part that I multiplied. This is R1 times 1/3. What am I supposed to do? I'm supposed to replace R1 times 1/3 into the first row. So let's rewrite this. X plus 2/3 of y plus 5/3 z equal to 73/3. Now, in this system, row 2 and row 3 are not changing. Therefore, I'm going to put those in here. Again, indented. This one isn't. You may have gathered that my plan is to indent each equation. In here, that one is indented. That means that the leading term has a different variable than the equation before that came before it, and also so that's one thing. And the other thing is that it's the variable that comes right after x, so we're actually sitting in a good place. I do not need to eliminate the term with variable x in the second row at all. But I see that the term with x exists in the third row, so I need to eliminate the term with x in the third row. So how do we do that? We use the equation with the leading term with that contains that variable, and we use the third row operation to actually eliminate that 2x in the last equation. So again, equation 2 was done for us. I don't need to do anything. What I'm looking at is that I don't need to do any interchange of any two rows neither, because at this point I'm just trying to eliminate 2x in the third row. This could have been sometimes using the interchange of two rows makes work a little bit easier, but not generally for cases that you're eliminating using the first row. So the next thing that I want to do is to eliminate 2x. How do I do it? I multiply the row that has leading term, leading one for the same variable, by negative of the coefficient of that variable, and then I add it to this row. What does that mean? That means row 1, that's the one with the leading one with this variable, multiply that by -2, then add it, this is row 3, and replace row 3 by that. Okay, how does that work? Row 1 times -2. This is row 1. This is our new row 1. So I multiply that by -2. -2x minus 4/3 y minus 10/3 z is equal to 146, -146 third. Then add the third row to it, 2x plus y plus 5z equal to 60. And so like term together, -2x plus 2x makes it 0x. Then here is y minus 4/3 of y. That is 1y minus 4/3 of y. 1 minus 4/3 is -1/3. and then multiply by 4, yy. In here, what do we have? We have negative 10 third of z plus 5z. Negative 10 third plus 5 is going to be 5 third. And so multiply by z. And then on this side is 60 minus 146 over 3. That is 180 minus 146 all over 3. 180 minus 146 is going to be 34 divided by 34 divided by 3. So now, what was this? This was row 1 times negative 2. Row 1 times negative 2. This one was row 3. I added them. This should be replacing row 3. So now I'm writing it down. X plus 2 third y plus 5 third z equal to 73 over 3 because row 1 was not changing. Then row 2. Then row 3 is going to be replaced by this. Okay, now notice that I eliminated x in all the subsequent equations using the equation that had leading 1 for x. The next step is to create another leading 1. So from here I see that the easiest leading 1 to be the more natural way of creating leading 1 is to divide this equation by 7 and then get another leading 1. Before doing that, I'm going to erase all this side of the board, and the next part of the solution will stay over here. Now we're continuing in row reduction process for this system. We're at the point that we created zeros underneath the first leading 1. Now what we want to do is to create another leading 1. And y is the natural variable to create a leading 1 for at this point. Let's see. Here, if I divide this equation by 7, then the leading coefficient becomes 1. So the next step is, again, see there is a pattern in here. Every time after elimination is done, to change the leading coefficient to 1, I just divide by the coefficient of the leading coefficient. So row 2 times 1/7 goes back to row 2. On piece of scratch paper, this is what I write. Row 2 divided by 7, which gives me y plus 1/7 z equal to 50 over 7. So let's go back in here, and I want to replace, so row 1 is going to stay the same. This is row 1, x plus 2 third y, 5 third z. Then this is the row 2. Then row 3 doesn't change. Now that we re-express the row 3, the next step would be to I have a leading 1 for x, leading 1 for y, and I have another equation over here. I need to indent this equation as well. That requires eliminating the first term, the term that has y in here, to start with the term that is not in any of the leading terms on the above. So what I do is, this is exactly the same process as when we were trying to eliminate 2x in here. Again, when we're eliminating, we use the row that contains the leading one for that, and that's the second row. Multiply that by negative of this coefficient, the leading coefficient, and then add it together to get a new row, row 3, such that this leading coefficient is going to be eliminated. Leading term is going to be eliminated. And so if you follow this process, you always start with the leading one, then eliminate that variable underneath, then these steps always work. And you can sometimes interchange 2 rows for making it easier on you if it's, let's say there are less fractions that you have to deal with or anything like that. It doesn't, and usually if you're not worried about the fractions, interchanging 2 rows doesn't really do a whole lot at this step. It does sometimes make a difference, unless the only thing that it may make a difference is that when you're eliminating, the indent goes away, and so the indent becomes opposite, and then you have to use the interchange 2 rows. So now the indent is the same for everything from now on, and the second row contains y, therefore I don't need to use the interchange 2 rows. So go back to what I'm supposed to do. I'm supposed to eliminate this term. That is row 3 plus negative of 1/3, which is 1/3. Row 2 goes back to row 3. Back to the scratch paper, let's write 1/3 of row 2. 1/3 of row 2 is 1/3 y plus 1/20y z equal to 50/21. Plus row 3. Row 3 is this one. Now let's add it. These two are supposed to, the way we set up the row operation was that these two supposed to cancel each other out. Now I need to add 1/21z plus 5/3z. That is we're trying to add 35/21 plus 1/21. That's 36/21 z is equal to, now, negative 34 divided by 3 plus 50 divided by 21. That becomes 288/21. So if I rewrite this entire thing, this is what we get. Row 1 stays the same, so I go back to the immediately last system that I wrote. Row 2 stays the same. And then row 3. Oh, nice and clean. Now I can actually see that the rows are indented. The only thing that is not matching the entire process is that the leading coefficient here is not 1. How do I make a leading coefficient 1? By multiplying by the reciprocal of the coefficient, the entire thing. So I'm going to erase that part, this part of the solution, finish the row reduction, then we start solving the equations. So the last step is to create a leading one over here. The indent is done. All I need to do is to create a leading one over here. And leading one creation over here when the indent is done is just R3 times 21 over 36 goes to R3. So on piece of scratch paper, what we write is 36 z over 21 equal to 288 over 21, and so it would be z is equal to 288 divided by 21 times 21 divided by 36, which would simplify to 8. So z equal to 8 is going to be the last row. And a lot of times that's what you see on the last row. You see just the last variable equal to a number. Let's rewrite everything. First row doesn't change. Second row doesn't change. Third row becomes. So now this is all indented, and all the coefficients are 1. This is your row, the reduced row form, which is, we call it reduced row echelon form. What I'm going to do next is, now that I have it in that format, I use back substitution to solve for y and to solve for x. And so how does that work? So how does back substitution work? What I need to do, since the last one is given, I will replace it back into here, and then I solve for y. So this would be y plus 1/7 times 8 is equal to 50 over 7. This gives me y is equal to 50 over 7. Subtract 8/7. And we get 42 divided by 7, which is 6. So now I solve for y equal to 6. Now replace. So if you notice, we started from the bottom. We went back. We replaced z, then we replaced y, then we found y, and now we should use z and y in the first equation to find x. So this goes in here, this goes in here, and we solve for x. So x plus 2/3 of 6 plus 5/3 of 8 is equal to 73 divided by 3. And if you solve this, it would be 73 over 3. subtract 2/3 of 6, which is 4, subtract 40 divided by 3. So after we subtract 2/3 of 6, which is -4, and then subtract 5/3 of 8, which is -40 divided by 3, we get x is equal to 43 minus 43rd is 33 over 3 minus 4, and that's 11 minus 4, and that's equal to 7. So x is equal to 7. And this is the solution for this system. One thing to remember, a system like this represents 3 planes in the 3 dimension. Therefore, the solutions can vary, but in this case, the solution only has one x value, one y value, one z value. So these 3 planes actually intersect each other in one point. And that one point is 7, 6, and 8. So I'm going to rewrite this. So now I can write the solution to this system is the triplet 7, 6, and 8, which is a point in the 3-dimensional space. Other notes, so the process was that we started by creating a leading one for the first variable that we could. Then we create indent underneath that for all the equations. Then we created another leading one for the next variable we could that existed in the system, and then creating indent for all the following, and continue all the way to the end. This is called the row reduction. There is another method that can be discussed. It's reduced row reduction. And so in that, so we create, instead of here, what we created right there is the row echelon form. We create reduced row echelon form. That's, again, is when we get to this point, we can use the last equation to eliminate all the terms with the variable in the last equations and the above. And then the second equation to use the leading one in the second equation to eliminate all the terms above, and so on and so forth. There are other methods of doing this. Is as you create the zeros underneath, you also create zeros above, which is how the computer does it. But for a course of for the first course in linear algebra, usually what you do is you create zeros underneath, and then you go back and create zeros above. So some of the statements that we make sense. I'm done with this example. What I want to come back to do is to show you that writing x, y, z is too much. So I'll introduce to you the matrices, and I redo this example using matrices and just doing the row reduction.